thanks for coming, and I really hope you enjoy the show.
Thanks, Matt. I'm going to use this. Does this help in the back a little bit? My voice is a little sketchy. Allergies, I don't know what. First of all, I want to say I'm really pleased to be back here. It's kind of a homecoming for me. 58 years ago, I attended my first Astronomical League National Convention right here in Milwaukee, or nearby Milwaukee. It was at the Hotel Schroeder, I think it was called. It's now the Hilton downtown, I believe. And an exciting event. It was full of young people. There were about 40 high school and college age students there. Something we're not seeing quite as much of, but your club seems to have a very good share of young people, and that's excellent news for the future. Your club is a founding member of the Astronomical League, one of just a couple that have been members continuously since it formed in 1946. I'd like to correct one thing. I'm vice president of the league. I was president back in 1998 through 2002, but he promoted me a little prematurely here.
I mumbled that.
I'm going to enlarge this a little bit. That's me with the big ears in the middle. Just to your left, this gentleman here is my oldest friend in the universe, Richard Gott. He's an astrophysicist at Princeton. And I've known him since I was 11 and he was 12. And we were both presidents of the local Junior Astronomical Society, which is a really prodigious organization back in the day when a lot of junior societies abounded during the space age. His name comes up a couple times in this talk. We talk every night at midnight, except when I'm traveling or something. And having a cosmologist that you can bounce things off of constantly is really an amazing thing. But I'll mention him a couple more times tonight. What we're going to talk about tonight are perspectives on distance, looking at questions like how far have we gone? How far can we see? How far can we expect to see in the future? And maybe even talk about the size of the universe a little bit. I do have a printed list of sources that I'll show you on screen a little bit later. And feel free to take one afterwards if you're looking for good reading about any of this subject matter. I had the ability to attend 3 moon landing Apollo launches. Apollos 14, 15, and 17. The last 2 from Merritt Island, from 3 miles away, thanks to a U.S. senator. And the launches were incredible to see. And they represent something that's important when we start talking about distance, and that's how far have we gone. And when you see moon launches like this, like Apollo 17, this was the mission, of course, when we launched the first scientist to walk on the moon, Harrison Schmitt, seen here. And one of the advantages of going to an Astronomical League National Convention is you get to meet people like this. Friendliest astronaut I've ever met, other than Story Musgrave. Absolutely incredible man. And he was on that last Apollo mission. Amazingly enough, the record for human travel, the altitude record for human beings, was not set by one of the lunar landing missions. It was set by one that didn't land, the Apollo 13 mission, an ill-fated mission. It suffered an explosion of an oxygen tank. And they set the record on tax day in 1970. 248,205 miles, partly because they looped around the moon rather widely instead of dropping into orbit, and because the moon at that time was near apogee. It was a little further from the Earth than perhaps normal, which, by the way, is what it's near today, which is why this eclipse was an annular eclipse, because the moon was a little further away and unable to cover the sun. Of course, our main target is Mars, and getting to Mars is a different can of beans. It's a little bit more difficult. Now, the closest Mars gets about 34 million miles, and I'm going to demonstrate that for you. I'd like you to imagine that what you're seeing here are the Earth and Moon, if I can get the button, 1 inch apart. I'll put it here so I sag the cord later. This is Mars at closest approach to the Earth. 1 inch apart. You can see this. Now I've made it a little too close to Mars. I did it, didn't I? And in the back, if you can turn on Mars at its furthest distance. It's hard to see with the light on back there, but you get the idea. Now this is when Mars is on the opposite side of the sun of the Earth. I'll take a look at it here on screen.
What are those two lights?
Okay. Here you can see Mars at closest approach, 34 million miles. And when it's on the opposite side of the sun from the Earth, and that arrow should stop here, not there. The distance, well, no, it shouldn't, it's right. 250 million miles. Now, which of these would make the shortest trip if you were going to make the trip? Which do you think would make more sense? 34 million miles, 250 million miles.
250 million.
Correct answer, 300 million miles. What? Why would we make the trip so difficult? Well, in point of fact, in order to go straight out to Mars, the closest approach, we have to undo 67,000 miles per hour of orbital speed that the Earth has around the sun. Otherwise, if we don't undo it, we just go flying off this way. So in order to make a straight trajectory out to Mars at closest approach and intercept it when we get there, we'd have to have enough energy, almost 3 times the energy that's needed in order to launch and escape Earth gravitation. Too much fuel. And there's another problem with it. And that problem is that we also have to climb directly out of the Earth's gravity well. Think of climbing a really steep incline. Is it easier to go straight up or to diagonal across like a switchback? Obviously, you use much less energy to make that switchback. So in the end, you use the same amount of energy, but it's easier on a per moment basis. So the way we'll go to Mars is like this. We won't climb directly out of the Earth gravity well, and we won't give up that 67,000 miles per hour. We'll use it to loop all the way around and intercept Mars, literally on the other side of the sun from where we started. It's called the Hohmann transfer orbit, and it's about 300 million miles long. It takes about 7 months, but it's the most efficient way to get to Mars in terms of energy consumption. Now, about 88 times further than Mars from us is the planet Neptune, currently the outermost planet in the solar system. If we were going to place an LED next to our Earth-Moon system here, it would be 1,000 feet away, probably around the entrance to the observatory grounds. Pretty far, 3 billion miles. And I'm using this to launch into a discussion of the furthest thing that we have ever sent into space. Humans have made it to the moon, but human-made spacecraft have now managed to reach a distance of 15 billion miles, 5 times the distance of Neptune. This is Voyager 1. It took 46 years to get to that distance. It's traveling still at over 38,000 miles per hour. Now, Voyager 2, which was actually launched before Voyager 1, a little trivia question there. Voyager 2 has not been slingshotted into space with quite the same velocity because it visited Uranus and Neptune. And so Voyager 1 will remain the furthest man-made object from the Earth. Even New Horizons will never overtake it. So the question becomes, what if we start talking about going to the nearest star to the sun, Proxima Centauri? Distance, 4.22 light years. That is 25 trillion miles, 25,000 billion miles. Now, Voyager 1 is not headed in that direction. But what if it were? 38,000 miles per hour. It's gone 15 billion miles in 46 years. If it were headed toward Proxima Centauri, how long would it take to get there? There's Proxima. And the answer is 75,000 years. If that makes interstellar travel seem difficult, it is. That's 750 centuries, about 12 times the length of all of recorded human history, just to get to the nearest star to the sun in the solar system. A really difficult problem. By the way, if on our Earth-Moon system here that are 1 inch apart, Proxima Centauri would be in Seattle, Washington. Okay. We live in a galaxy, of course, and if you have had the luck to get away from cities and see the core of the Milky Way, especially down in Aquila, Scutum, and Sagittarius, center of the galaxy as you're looking at it, how far are you really seeing? It's important to understand how big our galaxy is. I have a 50-cent piece here, just a 50-cent piece. And I'd like you to imagine that this was our entire solar system. The orbit of Neptune represented by the edge of the coin. The sun would be a bacterium in the middle. The Earth would be a small virus about a ½ millimeter away from it. On this scale of the entire solar system, the Milky Way galaxy would be the size of the North American continent and over 250 miles thick at the spiral arms. A little thicker at the center, of course. Now, when you see this Milky Way, you're not really seeing the core of the galaxy. You're looking from the sun into 2 arms, the Sagittarius arm and the Centaurus arms of the Milky Way, which block your view of the core beyond. So how far are you really seeing? When you look at that core, you're looking 60 quadrillion miles, 20 million times the distance to Neptune. But it gets worse. Now we have to talk about another little smudge that you can easily see in the sky if you know where to look in good skies. The Andromeda Galaxy, which is our big neighbor. It's in our little local group of galaxies, which is depicted here. It is the kingpin of our local group, which contains about 55 galaxies altogether. Here we have the Milky Way, 2.5 million light years apart. There's a third spiral galaxy called the Triangular Galaxy, M33 up here. The fourth and fifth largest galaxies in our local group are the Large and Small Magellanic Clouds, which are companions of ours. Now, how to emphasize the distance to Andromeda? Well, this is where Richard Gott comes up. Because one time I was having dinner at Richard's house one Christmas when he was back from Princeton to visit his parents. And apparently I made a comment that they took to heart. And the following year, I went to dinner over at their house again. And I could use the lights at this moment up front. Thank you, Matt. I went to dinner and Mrs. Gott, who was past president of the Garden Club, had this as her centerpiece. Now I smelled a rat because that was not her style. And all of a sudden, Richard unveiled a bowl of 1 million beads, scientifically measured, plus or minus 15 in count. And apparently I had made a comment the year before that I wish I had 1 million of something to show people. They apparently didn't realize I was talking about money. But anyway, this comes in handy because now I'm going to ask you to imagine that each of these beads, and this is heavy, that each of these beads represents 1 mile. So how many bowls of beads would I need placed side by side in a line in order to have 15 quintillion beads, which is the number of miles to the Andromeda Galaxy? Now think about that. Bowl after bowl, side by side, all touching. The answer is it would be a line of bowls extending from here at this table in Milwaukee to the planet Neptune. It's an incredible distance. And yet it's the closest major galaxy to us. So close, in fact, that it's not affected by this expansion of the universe. It's not being pulled away from us. It's actually moving toward us. We're attracting each other, and we'll collide in about 4.5 billion years. Thank you. Now, there is in the sky an area called the realm of galaxies. You don't see this on charts much anymore, but those of you who are amateur astronomers know that when you look into the regions like Virgo, Coma Berenices, Canis Venatici, Ursa Major, it's full of bright galaxies. Among the ones you see are these famous galaxies, M81 in Ursa Major, M101, M104, the Sombrero Galaxy, M51 in Canis Venatici, NGC 4565, which is a beautiful edge-on galaxy. And the core, or excuse me, a very, very strong radio galaxy, sometimes referred to as Centaurus A, NGC 5128, which is a little further south. But when you look in other areas of the sky, you don't see many bright galaxies at all. So why is that exactly? Okay. I'm going to ask you, I think I can stretch this. Okay, I'm going to illuminate the Milky Way and Andromeda. Once again, about an inch apart. Milky Way is the white one, Andromeda the yellow one. Now that's the 15 quintillion beads that extend from here all the way to the planet Neptune. 2.5 million years for light to transmit between those two. And here are a few of the others. If I can find the buttons. Centaurus A, it's M101. Okay, 51, and that will do for those. And what you see back here, these large spheres, represent clusters of galaxies. This large one, this big yellow one here, represents the Virgo cluster of galaxies. It's 55 million light years from us in this direction. Ursa Major, Canis Venatici clouds. These are major clouds of galaxies, but it extends in a filament that ends out here with the Sculptor galaxy, the silver coin, it's called, NGC 253. Now notice what happens if you look up in this direction. You see lots of bright galaxies, famous ones lighted here, and clusters of very bright ones in the background here, especially when you look all the way to the Virgo cluster, which is seen here. Bright stars have been blotted out to avoid glare. You have, of course, the giant elliptical M87 here, Markarian's chain here. All of these are easily seen in 6-inch telescopes, maybe smaller, even 3-inch, maybe 2.4. Okay, and the reason is because you're looking up this chain. But this chain sticks out into a void in the direction of the Sculptor galaxy. So they call it the Sculptor void. Okay? This is the silver coin that's looking past the end of this chain of galaxies. And here it is kind of demonstrated in 2D. Milky Way at M31. And you look up the chain, lots of bright galaxies in that direction. Look in the other directions, though, and you're looking into voids, giant voids. One of them is the Sculptor void. That would be in the direction of that Sculptor galaxy, 115 million light years across. The biggest one, the Boötes void, is over 300 million light years across. And what you're seeing now is the entire Virgo group, represented by this model, reduced to just this. Here you have the Milky Way, Andromeda, Canis Venatici cloud, and the Virgo cluster, connected to a big structure here, and then two other filaments running off in different directions. Of course, I can't show this to you in 3D, but it would be three-dimensional. And what you're seeing here is 250 million light years across. It's called Laniakea, which means in Hawaiian, immeasurable heaven. But like I just mentioned, we've measured it. So that is the local supercluster. And as you back away, you see the extension from the Virgo cluster to us, the Sculptor void, and now you start seeing a pattern. You start seeing something called the cosmic web, filaments of galaxies draped through space like a spider web in 3D. You can back away a little more to about 10 billion light years rather, and see the structure of the galaxy. The first person to propose this structure was Richard Gott, my friend of many, many decades. This was taken in French Lick in 1998 when he received the Astronomical League Award from us. And this is from his 1986 paper, in which he was the lead author on the paper with two other scientists who proposed a sponge-like structure to the universe. That is to say, think of a block of cheese, one in which a bug could eat its way all the way through the block, or a bug could fly through the holes all the way through the block in any direction. The holes, the voids are all connected, and the sheets of galaxies are all connected as well. So he came up with that idea, and it was a brilliant idea. Whoops, sorry. Now the question becomes, well, how far can we see? You probably think we're out of the range of what you do as amateurs. And if I could get Dhruva to assist me with one more illumination in the back of the room. There we go. Now I'd like you to look back up here. This is the Virgo cluster, 55 million light years, the realm of galaxies. What's represented here is about 47,000 galaxies altogether. And on this scale, if I pick this up and aim the Virgo cluster in that direction, that would be where 3C273 is. It's a quasar that you can access in a 6-inch telescope with no problem at all, probably a 4. It's about magnitude 12.9. What you're seeing is an active galactic nucleus, one in which a supermassive black hole is accreting material from stars that have been victimized by it. The material is swirling around faster and faster as it nears the event horizon, and the friction creates huge jets of radiation that allow you to see it all the way across the cosmic web in sort of this kind of a diagram. But you can do better. There is a quasar that I recommend to you because it's easily seen in 10 and 12-inch telescopes. And it's easy to find because in the field of view, you have 2/8 magnitude stars. Leads to a nice triangle of 11th through 13th magnitude stars, and off to the side, 3 14th magnitude stars. The third one in this little arc is the quasar, and its light travel time. The length of time that that light has been traveling to you when you see it is 9.6 billion years. That's about twice the age of the Earth. That entire time it's been traveling, and you stop it when you see it. And it's not that hard to see. You have to use a little averted vision, a smaller telescope. It's a little bit fainter than Pluto is in a telescope, but with a 10 or 12-inch and reasonably good sky, you can access it. What you're seeing when you see it is an object whose light has traveled 5.6 septillion miles. Yeah. Now, I don't know how to describe a number like that. It's very difficult. I will tell you that that's a number that is greater than the number of stars in the entire observable universe. It's pretty far. It's 2 trillion times further than Neptune and 200 million times further than that nearest star, Proxima Centauri. And this is what you're seeing. You're seeing light that has taken 9.6 billion year path to get to us. By the time it got to us, though, the universe had expanded. And so today, that galaxy, that quasar, is at 12.9 billion light years. That's where it actually is today. And you can do even better. With an 18 or 20-inch telescope, many of you have access to DOBs of that size. You can see a magnitude 15 quasar called APM 08279525 in Lynx. Its light travel time to you is 12 billion years. Now, bear in mind the universe is 13.8 billion years old. So this light has been traveling literally across the entire observable universe and is accessible in amateur instruments. It's really incredible. Its current distance from us, 23.6 billion light years. I will tell you that that is so far that the galaxy today and we are being separated at almost twice the speed of light because of the expansion of the universe. Now, if you're wondering what the furthest thing we've ever seen is, The current record holder is this. This is something that was picked up by the James Webb Space Telescope. It's called HD1. You don't have access to this, but this is the record holder for furthest object that we've ever observed in the universe. Light travel time, 13.5 billion years. Current distance is 33 billion light years. Okay, so this light has been traveling to you for nearly the entire age of the universe, which means that you're seeing this galaxy as it was when the universe was only 300 million years old. That's just 0.3 of a billion years. You're practically looking back behind the time when stars formed. So we don't expect to see things that are much further. We may build bigger space telescopes so we can see things like this better, but we're not going to see much further because there's only so far back in time you can look before you're looking back into that dark age before stars formed. Let me try to explain what you would do. Let me go back to HD1. Suppose you and a friend were looking at this through some magical telescope, looking at it live. And your friend asked you, how far is it? What do you answer? I will tell you that there are 3 possible answers you can give. The first possible answer is 1 billion light years, because that's how far away it was when it looked like this. When the light left there and started heading toward whatever was going to become us, it was only about 1 billion light years from us in a much smaller universe. Okay? Another answer you might give is 13.5 billion light years, because that's how long the light took to get here. And another possible answer you could give would be 33 billion light years, because that's where it is today. But think of the problems that all 3 of these distances have. It clearly can't be 1 billion light years away because the light took 13.5 billion years to get here, right? We know how fast light travels. Can't be 13.5 billion light years away, because if we could magically transport ourselves back up the light path instantaneously, 13.5 billion light years, there'd be nothing there. And we know it's 33 billion light years away today, in whatever form it has today. But how could that be if the universe is only 13.8 billion years old? You see the problems that astronomers have. And so what astronomers do is they just say, we're just going to give you the Z number, in this case, 13.27. And that number means that the light has been stretched. It's been traveling through expanding space-time long enough so that the wavelengths of light that left there have been stretched 12.27 times, not 13. Okay? Now, to make this a little easier to understand, I'd like you to imagine that Dad has taken his daughter to teach her to swim. This dad's not going to do what my dad did, which is back up the whole time I'm swimming to him. This dad's just going to stand still 10 feet away, and his daughter Emily, who's going to be our photon, leaving HD1, and HD1's going to be this wall here. And she thinks, well, this is easy, just a couple strokes and I'll be there. So she starts swimming. The trouble is, this is a magic swimming pool. The walls constantly get further apart. The bottom stretches, extra water is sprinkled in to keep the depth up. So she starts swimming the 10 feet, and she swims and swims and swims, and she finally gets to Dad, and she's ended up swimming 100 feet. And then she looks over her shoulder, and the wall's 300 feet behind her. That's HD1. HD1 was 1 billion light years away when the light left there, when she let go of the wall. The light ended up traveling 13.5 billion light years, 100 feet. And by the time it got here, the wall had receded. HD1 had receded to 300 feet, or 33 billion light years. That's the problem with a dynamic universe. It's very difficult to conceptualize. Now here, I'm going to use some charts just to try to explain what horizons exist on what we can see. What you see here is a bright blue circle. It has a radius of 13.8 billion light years. That's the furthest distance from which light has had time to travel to us in the 13.8 billion years the universe has been around. There's HD1. Its light path is 13.5 billion light years, and today it's out here at 33. All the other galaxies that we see are closer than that. Remember, HD1 is the record holder. They all have shorter light travel times to us, and they're closer to us, in fact. Most galaxies, of course, as you go out, the volume of each shell of distance becomes bigger. So most galaxies that we see are out here. Millions of galaxies, billions of them actually, are much further out. The closer you get, you see fewer of them. The furthest possible thing that we could see, if you could imagine hypothetically, that something was shining the minute the universe became transparent shortly after the Big Bang, and whose light needed all 13.8 billion years to reach us, that object today would be at 46 billion light years. And that is the distance that astronomers call the edge of the observable universe. Okay? Nothing was shining 13.8 billion years ago, so we don't see any galaxies that we know are 46 billion light years away. But that's the hypothetical limit. Edge of the observable universe, 46 billion light years. Think of it this way. And every place in the universe has its own observable universe with the same radius, same age of the universe everywhere. Some of them overlap with ours. Okay? Now, what if you had a galaxy here, let's say 15 billion light years? By the way, this yellow line you see here, that represents something else. Because of the expansion of the universe, 14.4 billion light years, the Hubble distance, we'll call it, is the point at which galaxies are being pulled apart because of the expansion of the universe at the speed of light. This doesn't violate special relativity. It just means that two galaxies sitting still in space are being pulled away so that they're receding from each other at the speed of light. So what if we have a galaxy out here at 15? The first question I have is, can you see it? Can you see something that is being pulled away from us faster than the speed of light? How could the light get here? Well, the answer is, of course, we can see it. We can see HD1, it's way out here at 33. We simply see its old light that left when it was much closer to us. But what if a supernova went off in this galaxy today? Would that light ever reach us? Seems like it wouldn't be able to. But in point of fact, it can. Because even though it and we are separating at greater than the speed of light, our Hubble distance and it are not. And so those photons can make it inside our Hubble distance. And once they do that, they can make it the rest of the way. But this only works out to 16 billion light years. 16 is the limit. At 16, the light can barely make it inside our Hubble distance, and hence the rest of the way. We'd have to wait billions of years in the future to see that supernova if it occurs today. Anything beyond 16, there's too much space expanding between it and our Hubble distance. We're never going to see it. So 16 is called the cosmic event horizon. It is the distance beyond which an event occurring today or recently will never be seen by us, no matter how many trillion years you wait. Interestingly, that means that everything beyond 16 billion light years is unreachable. We can't send a light signal to them. They can't send a light signal to us. You can fire up the Enterprise at warp 1, you're never going to get there. Okay? But look at this. Most galaxies that we see are already unreachable. 96.7% of all the galaxies you see when you look at that Hubble deep field are already unreachable. That means the last photons that will ever get here from those galaxies left there long ago. You're never going to see anything that happens in there today. Very difficult problem indeed. So the magic question is, how big is the rest of the universe? And I don't want to get into anything super complex here, but it depends on basically the geometry of space. And the Planck satellite has done the best job of analyzing the cosmic microwave background, the heat from the original Big Bang, to try to determine whether our universe has what they call open curvature, or is flat, or is closed. Now, an open universe is infinite and has been infinite from the beginning. And it can be, that can be. Most astrophysicists I talk to believe it still is, even though the Planck satellite says it's perfectly flat with a margin of error of 0.4%. That's 1 part in 250. Hold that number in your mind. If it's perfectly flat, which seems unlikely because it would be sitting on a razor's edge, then it would become infinitely large in an infinite date in the future. But if it's closed, and the only analogy I give you to a closed universe that's unbounded is the surface of a sphere. The surface of a sphere has a definite surface area. It's finite, but it has no edge. So if you can conflate that with three-dimensional space, you'll have an idea of what I'm talking about. If it's closed, it would be finite, but how big? And this is where that 0.4% comes in handy. If the universe is closed, and it's unlikely to be, if it's closed, the minimum size it could be is 250 times bigger in diameter than our entire observable universe. That would be 15 million times larger in volume than the volume of our observable universe. And that's the smallest it could be. Alan Guth, Andre Linde, who are two of the leading inflationary cosmologists, estimate, Guth says 300 sextillion times larger if it's finite. And Andre Linde said it could be as large as 10 to the 40,000th power times larger if it's finite, if it's closed. But again, most astrophysicists believe it's open or possibly flat. So there is a minimum size, and that minimum size is 15 million times bigger than that sphere of space with a radius of 46 billion light years. By now, I suspect you're feeling somewhat small. So I'd like to start by talking about, and this is the conclusion, why you probably shouldn't. The smallest meaningful space, unit of space, is called the Planck length. It's about 1.6 times 10 to the minus 35 meters. To say that that's tiny, it's about 100 quintillion times smaller than a proton. Give you an idea. To probe below the Planck length, you would have to import so much energy to that little distance that the energy itself would cause whatever you're examining to become a black hole. Laws of physics break down there. It is the point where quantum uncertainty becomes 100%, and so we can't know anything below the Planck length. But let's suppose we take the Planck length and start doubling it. 2, 4, 8, 16, 32. Just keep doubling it as we go. It turns out that we have to go 202 doublings before we get to the size of the observable universe. The median-sized object there at 101 doublings, are the little dust grains you see floating in a sunbeam, which happen to be, ironically, the smallest things you could observe with the unaided eye. That's the median-sized object in our observable universe. You come in 16 doublings larger than that. So you're not so small after all. And I think that's important to understand. I have here an object which I commend to you. It is a 1 cubic inch block of tungsten. It's very heavy, one of the densest elements there is. And when you feel it, you'll understand what I mean. I've always wanted to order a 4-inch block of it, be about the size of a softball, and just see the expression on the UPS person who brings it to the house weighing 42 pounds. Okay. But the interesting thing about a block of tungsten with 1 cubic inch is it has almost exactly 1 septillion atoms in it. Now think about that. There are more atoms in this tungsten than there are stars in our entire observable universe, 2 trillion galaxies worth. And it's empty space, just like the universe. The amount of empty space in here is 99.999,999,9996% empty space. So, universe. You're pretty big in comparison to this. So I hope I've given you some perspective on just how big things are and why you shouldn't feel too small. And I really appreciate your coming tonight, even though there's no observing. I enjoyed it a great deal, and I'll be happy to answer questions either openly or up here afterwards. Thank you very much, Matt, for all you've done in arranging this and for all the work you do for the MAS. extraordinary club, and I commend you to join it because there are no clubs better anywhere in this country for longer servants of astronomy education. Thank you very much. It's the first time I've ever heard that.
So I do have a question. So
Yes, sir.
as we talk about, you know, this, I can't remember what that visible boundary was, right, of what we could see of the universe, and that it's continuing to move away. So if I think of a time frame over billions and billions of years, will I expect to see fewer points of light in the sky?
Excellent point, and you're absolutely correct.
Yeah.
One thing about horizons that you have to understand, we live in not only a universe that's expanding, but we now know from supernova studies that earned a Nobel Prize that it's accelerating in its expansion. And the faster it expands, the harder light has to reach us from a given point. And so as the universe accelerates, these horizons move in on us. And there's some thought that if the universe does continue to expand forever and accelerate forever, that it leads to an ending called the Big Rip, which results in galaxies not being seen beyond our local group, and then ultimately could even pull apart galaxies, pull apart solar systems, pull apart atoms, and end things. You can read about it. It's called the Big Rip. It's a theory. No one knows if the acceleration will continue forever. There are a few people out there that even doubt it's accelerating, but it's generally understood that it is. The supernova studies were extraordinary work. What they did is they looked at supernovae that were close to us and supernovas that were at great distances from us. And they expected to see a linear function, you know, in terms of the stretching of the light from these supernovas. And they didn't. And so as a result of that, they were able to determine that the ones that are closer seem to be winging their way from us faster than they should be, and the ones that are further, not so much. And that suggests that more recently the universe is accelerating faster. And so you're absolutely right. It will eliminate your ability to see greater distances as those horizons move in. Long-term future. You don't have to rush out and observe right now, you know.
So eventually you're saying like there's not going to be really any lights in the sky, or much fewer lights in the sky at night.
Well, yeah, as the horizons move in, yes. Now there's going to be a period of time as the universe gets older, light from galaxies that has needed 14 or 15 billion years to reach us will appear. Okay, so there's going to be an increase in the short term of galaxies that we're able to see as the universe ages. But then eventually that stops, and then the galaxies start getting redder and redder. Their time seems to slow down, and they just wink out. We just don't get any more photons from them. And we're not getting any photons that are leaving 97% of those galaxies now. And in fact, that left there a billion years ago, for that matter, or even two. Yes. I'm sorry, I couldn't. Flat?
What do you mean by a flat universe?
A flat universe would be one in which if you connected three stars with lines, made a triangle, the triangle would have exactly 180 degrees in it. If it's an open universe, it would have less than 180. You'd have to liken it to the surface of a saddle. Like if you drew a triangle on a saddle, it would have less than 180. On a sphere, you draw a triangle, it's going to have more than 180. That would be a closed universe. So what they've done is they've started examining what are called anisotropies, which are the temperature variations in the microwave, the cosmic microwave background, expecting to see them to be a certain size if the universe is flat. But if they're too large or too small, that would indicate open or closed. And that's the magic thing these satellites, starting with COBE, WMAP, and now the Planck satellite, have been trying to determine. And every time they come out perfectly flat. That could be because inflation just blew the universe up so big in the first decillionth of a second after the Big Bang that it just seems flat to us still. But there is that 0.4% error that could be either side. And no one can answer that yet. Okay. Anything else? No questions.
I have a question.
Yes.
You mentioned observing a quasar. Now, I understand there's an Astronomical League observing program to
Yes.
look at quasars. Could you tell everyone a little bit more about the observing programs just
Yes.
like it that might help them observe these objects?
We started our observing programs in 1967, and with the Messier Award, you observe all 110 Messier objects, sketch them, and you get a pin and a certificate and national recognition in our newsletter, in our magazine. That's now grown to over 80 programs. There are 35 coordinators of these programs who handle, the certifications and send out the pins and certificates. I do 3 of them. And they're immensely popular. To date, we've given out over 16,700 certificates to over 6,000 different people, discreetly different people. And the programs are immensely popular because when people start into them, I've done 43 of them, when you start into them, you are driven to observe things that you just would not get around to observing otherwise. Variable stars. Maybe none of you have done that. This encourages you to do that. Maybe observe Jovian moon transits and eclipses. Maybe observe quasars. Maybe observe galaxies in a given program. Observe planetary nebulae. Observe emission nebulae. Observe dark nebulae. Solar work, both white light and H alpha observations, and on and on. And so it really gives you, plus there are a lot of binocular programs in conjunction with this. We have 10 now, binocular programs, which are a lot of fun, very relaxing to do, and also interesting, including a binocular variable star program. And I encourage you to try one or two because I think you'll find they're quite addictive. And they will drive you to not observe the same old every time you go out, which a lot of amateurs still do. I know a friend with a 20-inch Dob. I think he looked at the same thing, the same 5 objects every time he went out. And I said, you've got something here that's capable of looking all the way across the observable universe. You ought to turn it on that. Anything else? Thank you again. Been great.